Think about the everyday act of claiming a new handle on a popular app. You type in your desired name, click submit, and a confirmation ripples across servers distributed all over the planet. But consider the geography of that request. If you are in New York and a user in Tokyo hits enter on that exact same handle at the exact same millisecond, who gets it? The physical internet is bound by the speed of light, meaning your data reaches local servers long before it reaches Tokyo. This diagram represents a concept called linearizability. It forces a sprawling, multi-continent database to behave as if there is only one single copy of the data. Under linearizability, every operation happens in a strict timeline. The network tracks the sequence so tightly that a subsequent read will always return the most recent write. If engineers fail to maintain this strict sequence, two people claim the exact same account. Bank balances double spend. Without a way to agree on a single timeline, the rules of digital scarcity and unique identity simply stop working. Maintaining that illusion is incredibly difficult because the physical internet is chaotic. Underground cables get cut, routers drop packets, and servers abruptly lose power. Eventually, a cluster of servers in Europe will lose its connection to a cluster in North America, a geographic split known as a network partition. In this diagram, the solid barrier represents that severed connection. When a user requests data during this partition, the database hits a mathematical wall called the cap theorem. It must make a strict choice, either lock up and wait for the connection to return, ensuring accuracy but appearing broken to the user, or immediately serve the user whatever data it has, even if that data is out of date. To preserve the illusion of a flawless single machine, without completely freezing every time a wire trips, these isolated computers require a resilient mathematical mechanism. They need a way to build a shared reality. The most intuitive way to get a group of computers to agree is to demand a unanimous vote. Historically, databases tried to achieve this using a protocol known as two-phase commit. Watch how this diagram operates. In phase 1, a central coordinator node pings every single satellite database and asks, "Are you ready to record this transaction?" It then waits to collect a green checkmark from every single machine on the network. But look at what happens if that central coordinator suddenly loses power before sending the final commit command. The satellite nodes freeze in place. They place padlocks on their local data, waiting for final instructions that will never arrive. Because the system promised a unanimous decision, no individual node can safely cancel the transaction or proceed on its own. The locked data becomes completely inaccessible to users. Requiring every single machine to report in perfectly is a liability. For a network to survive crashes, it needs a voting mechanism that can drive forward even when individual machines go dark. Modern distributed databases abandon unanimity. Instead, they rely on a lower threshold, simple majority rule, powered by consensus algorithms like Raft. This animation illustrates how Raft works. The nodes hold an internal election and promote one server to act as the leader. This singular leader now dictates the order of all incoming actions for the group. As the leader pushes a new block of data outward to its followers, it does not wait for perfect attendance. The exact moment 50% plus 1 of the active nodes log the data, the decision is mathematically finalized and stamped as permanent. If that leader crashes a second leader, the system doesn't freeze. The followers realize it's gone, immediately hold a new election, pick a replacement, and resume operations. By funneling requests through a leader and counting majority votes, Raft forces every machine in the cluster to record every action in the exact same chronological order. Computer scientists call this total order broadcast. In distributed systems theory, if a network can reliably agree on the exact sequence of a chronological log, it has solved the problem of consensus. The independent machines act as one. But enforcing agreement requires constant, heavy communication. Gathering a majority vote from servers spread across multiple continents adds hundreds of milliseconds of delay. The math also demands a strict minimum headcount. If a massive outage knocks offline exactly half of the servers, achieving a majority becomes mathematically impossible. To prevent corrupted data, the system protects itself by rejecting any new writes until machines come back online. Because it requires intense communication overhead and carries the risk of stalling the network, engineers cannot afford to use strict consensus for every everyday database read and write. To build fast applications, engineers quarantine this heavy math. They offload the complex voting logic into dedicated coordination services like ZooKeeper or etcd. Look at this network map. The vast majority of the application runs on fast, highly available data streams that tolerate slight delays. But clustered in the center is a tiny, highly guarded group of servers. They act as a specialized brain, processing only the most critical agreements. Linearizability is the illusion of a single machine. To achieve it, the network requires strict ordering, powered by the majority voting engine of algorithms like Raft, and carefully managed within those dedicated coordination services. The seamless, immediate internet we navigate every day is not a default setting. It is a highly engineered feature, bought and paid for by rationing a few carefully chosen, mathematically sound agreements.